Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations, and we're going to look at one of the very interesting methods called finite different method. So this is completely different from the methods, basically the general runge-kutta family that we have talked about so far. So in the finite difference method is that the idea basically is that we want to solve the differential equation on a grid, and most of the time it's a uniform grid because it's just easier to deal with uniform grids. And what we do if we want to solve from x0 to xn, right? And basically in the previous methods or general runge-kutta families, we said that if we have, for example, an initial value problem for an ODE, so at x0, y0 is given, and then at later point, let's say xn, we had to create a sequence and iterate through the sequence until we get a good accuracy for xn, right? But then if we want to find the solution at n points from x0 to xn, we have to do the same iteration for every single point, right? So in finite difference, it's not like that. In finite difference, what we do, we convert the differential equation into a system of equation, basically an algebraic equation. And if the differential equation is a linear ordinary differential equation, i.e. if I have y prime equals f of x and y, then f of x and y is linear, then I end up with a linear system of algebraic equation, and that's very easy to solve. And in most of the physics problems or engineering problems, the differential equations are in fact linear, so that's the advantage, right? So the idea here is that we set the values of y1, y2 all the way to yn as variables or unknowns that we want to find. And then based on these values that we don't know, we discretize y prime, all right? So yx becomes a vector, over this grid becomes a vector of values, right? A column matrix or a row matrix. Typically a vector is a column matrix, right? So here we're dealing with matrix algebra. So y of x becomes a vector of y0, y1, y2 all the way to yn, so n plus 1 components. And then y prime equals f of x and y can be either an initial value problem, a final value problem, or a boundary value problem specified over a and b. A is x0, b is xn, all right? So initial value or final value problem, and then we divide into n sub-intervals, right, from x0 to xn. So our grid, the size of our grid is actually n plus 1 nodes or points, right? And then the key here is to discretize y prime based on these unknown y values, the exact values of the function that we do not know, but we want to find them. So y prime, let's say the easiest way is to do a forward discretization, forward difference. So y prime at xi is 1 over h. H is the step size, which is our delta x. Y of xi plus 1 minus y of x, right? So at y0, y prime 0, y prime at x0 is y1 minus y0 over delta x. At x1, y prime at x1 is y2 minus y1 over delta x, etc. So we discretize. And then if we do that and we substitute here, we end up again with a similar sequence with in general a nonlinear system. So similar to Euler method, if you recall, in the Euler method we did exactly the same thing, but here instead of generating a sequence that converges to the value of the y at each of these points and then doing it n times, we're going to actually create a system of n equations, right? So we put this for each of these points. We actually end up with n plus 1 equations, not n equations. Depending on whether we have initial value, final value, we have to remove one of the equations, and I'll talk about it in the next slides. So we have boundary conditions, initial value or final value, both of them are possible. And then we solve the nonlinear system, use our particles form optimization, which we already seen. If it's a linear system, we don't use PSO or any kind of Newton-Raphson method. It's a very easy to solve a linear system, and I'll talk about it in the next slides. Alright, so what's the benefit of finite difference method? We already have very nice runge-kutta methods for ODEs. So, I mean, finite difference method, first of all, it's mostly regarded for linear ODEs, right? For initial value problem, it's best not to use it. We already have runge-kutta methods. For boundary value problem or final value problem, it's an alternative to the shooting method. So if you recall, in the shooting method, we said that if we do not know the initial condition, but we know the final condition, we can we can do a root finding for the initial value by solving the ODE and finding the value at the final point, and then finding the initial value such that the final point actually becomes the final value that we are given. And then after finding the initial condition, we can solve the ODE based on any of the runge-kutta family methods, right? But for the eigenvalue problems, if you recall, eigenvalue problem is like the basically the differential operator acts on a function y and it becomes some number times y, right? And we do not know what that number is. For this type of problems, finite difference method is great, because you translate the differential equation into a matrix equation, and for matrices, finding the eigenvalue is super easy. We already know how to find the eigenvalues of a matrix, and the eigenvalues of the differential equation are exactly the eigenvalues of the matrix problem. So that's very easy, and that's great. So, and the other thing is that transforming the differential equation for an eigenvalue problem into a finite difference method or a matrix equation, then it can also give all the eigenvalues simultaneously, because when we solve for the eigenvalues of a matrix, we find them all together, right? And then for linear ODEs, we said that the finite difference method translates nicely into a system of linear equations, algebraic equations, and it's very easy and very numerically efficient to solve a linear system of equations. Now the key here is that how do we translate the problem, the original y prime equals f of x and y, into a matrix equation or a system of algebraic equations. The way we do it, again, we discretize the y primes over the grid, and then our y function becomes a vector of n values, y0, y1, y2, all the way to yn plus 1. So we have n all the way to yn. So we have n plus 1 components, right? And we either know the value of the y0 because we're solving an initial value problem, or the value of yn because we're solving the final value problem. So one of these two is known, right? So we do not end up with n plus 1 equations. One of them is going to be redundant anyways. And then if we do this and use the forward difference discretization for y prime, we see that the ddx of y of x. Now y of x becomes a vector, right? y0. This ddx becomes a matrix, 1 over h. So basically y0 prime, this ddx of y of x should give me a vector which has the values of y0 prime, y1 prime, y2 prime, yn prime. So y0 prime or y prime at x0 is y1 minus y0 over h. So the first row is 1 over h minus 1 and 1, right? Minus 1 is multiplied by y0, 1 is multiplied by y1, and the rest are 0 because they do not appear in the y0 prime. And again, this way we can construct this matrix that when is multiplied by the vector of y values, it gives me the vector of y primes based on our discretization, right? So we call this matrix the Diff Operator, or the Diff ddx matrix operator. And it's a very nice matrix. Based on the forward difference approximation, all the diagonals are minus 1, all the upper diagonal are 1, and then there is the coefficient is 1 over h, or 1 over delta x, right? The step size. Okay. So that's our diff operator, and then we can translate any linear differential equation using this diff operator. For example, the second derivative becomes dx, this matrix, times itself, dx, right? And it gives us minus 1, 1, minus 1. It gives us probably 1, 2, 1, 1, minus 2, 1 or something. All right. And typically when we're dealing with matrices, it's easier to use the notation of Kronecker Delta. So Kronecker Delta is just 1 when the indices are exactly the same. And it's 0 in other cases if the two indices are not the same. And therefore the elements of this dx matrix, the ijth element is 1 over h. For the diagonal, we end up with minus 1 times delta ij. So this term is minus 1 if and only if I is equal to j, or the diagonal element. The next one is I and j minus 1, or when the column is I plus 1. For example, here this one element is row 0, I is 0, j is 1, right? Let's start indexing the rows and columns from 0. So 0, 1 and row 0. So when I is 0 and j is 1, we end up with delta 0, 0, which is 1. So all the upper diagonal elements are delta I, j minus 1. And all the diagonal elements are minus delta ij, all right? And that's how we can easily construct this matrix in our programming, okay? So again, this diff matrix depends on the way we choose to discretize y prime. So based on the forward, this representation minus 1 diagonal and 1 upper diagonal is based on the simple forward difference approximation, all right? And it works great, so we do not need to go to the higher or better approximation. We just increase the number of points, or basically reduce the, basically we increase the size of the grid or increase the number of discretizations. That gives us a better and better accuracy, all right? Now, how do we actually solve differential equations, ODEs, with this method, with this finite difference method? So the idea is that, okay, we have n plus 1 equations, but based on the conditions of the differential equation, either initial value or final value, one of the equations is redundant. We do not need that. So for an initial value problem, y0 is known, right? And for a final value problem, yn is known, right? So if I'm solving an initial value problem from this matrix, so eventually we transform our system into a matrix, which some matrix times the y vector equals to some vector that we already know the values based on the x. And this decomposition happens for linear systems, any linear ODE. So from now on, let's just assume we're talking about linear ODEs. So if I know the value of y0, basically an initial value problem, right? I only have n unknowns, y1, y2, all the way to yn, right? So for an initial value problem, I need to remove the first column and the last row and solve a system of n equations from row 0 to row n minus 1 and from column 1 to column n, right? So n equations. And then if the thing is that then look at the first row is minus y0 plus y1, right? So what I need to do, I need to take this coefficient multiplied by y0 and bring it to the right side of the equation, because I already know whatever values that I know from the y vector, I have to remove them from the left hand side and bring them to the right hand side, all right? So for an initial value problem, we remove the first column and the last row, and then take y0 to the other side of the equation. That's how, so basically we form our matrix equation, and then we have to apply our boundary conditions, either an initial value condition or a final value condition. And the way we do it, the way we apply it to our system of equations is that we bring the known values from y to the right hand side and set the coefficients that multiply by those values to basically we just remove those corresponding rows and columns, all right? Now for a final value problem, the value of yn is known. So I have to solve for y0, y1 all the way to yn minus 1. So I have to keep the first n rows, right? So I have to remove the last column. So we remove the last row and last column. And then what we do from the n-1 row, this row, we bring yn to the other side. So basically this coefficient here, 1, we have to bring it to the other side. All right? So this becomes more clear when we look at an actual problem and look at the code. But basically the idea here is that applying the boundary conditions means that we remove the corresponding rows and columns, and then bring those values, rearrange the equations or modify the equations to bring the known values to the right hand side. All right? Now the question is, why do we go through this finite difference method? Didn't we already have like very nice, elegant runge-kutta methods? And the reason is that the runge-kutta families are specifically defined for ODEs, ordinary differential equations. As soon as we go to the partial differential equations, they don't really work, but the finite difference method actually works. So finite difference method, the idea is discretizing over grid, and this grid can be a one-dimensional, which is what we're doing right now, right? One-dimensional grid is basically solving an ODE. But a two-dimensional grid corresponds to a partial differential equation, and a three-dimensional grid corresponds to a partial differential equation. So the concept of grid very nicely scales to higher dimensions, but the concept of runge-kutta method doesn't really work like that. All right? So that's why finite difference method is a very, very popular method when we are solving partial differential equations. So again, based on a discretization, we create the representation of the Diff operator, and the higher order differential or higher order derivatives are just multiplying the matrix dx by itself, right? Simply just multiply matrices for higher order derivatives. So how do we create this dx matrix? So basically it's a Java class, and I have a method here built dx. So the coefficient is 1 over x, or 1 over delta h. And then we iterate through the rows and columns, and deem the dimension of the matrix is n+1, right? And then dx ij, the ij component, it's just much easier to use the Kronecker Delta notation. So I defined a method called delta Kronecker, which takes two integers. If the integers are equal, it returns 1. Otherwise, it returns 0. It's a very easy method, right? And it's a static method in my math utils class. So coef is 1 over delta x, or 1 over h, and then minus the diagonal matrix minus delta ij plus delta I plus 1 and j, right? I plus 1 and j, or I and j minus 1. Both are equivalent. Alright, here's an example. Y prime equals minus y plus 2x. Now obviously this is a linear function, right? So this is a linear ODE in terms of y and y prime. And we want to solve it over the interval x equals 0 to 10 with the initial condition of y0 is 1. So this is an initial value problem. So we consider y as a vector, capital Y, that holds the values of y0, y1 all the way to yn, right? So we have to specify n, or the number of the size of our grid, which is n+1. So here's the code. X0 is 0, so we're solving initial value problem. X1, or maybe let's call it xn, is x0 plus 10, right? This is the final value, final point, and y0 is 1. Our grid size is 501, and grid size is n+1, remember that? And we're going to discretize, create our matrix of x values, linear space, uniform grid, so linear space x0 to xn, and grid size. Remember, we have to have n+1 points, right? So n here is 500, for example, and this method linear space returns a one-dimensional array, and when we assign it to a matrix, it automatically transforms it into a row matrix, a one-dimensional row matrix. So this x vals is a matrix, And then our step size is just x vals get elements 0 1, so row 0 column 1 minus row 0 column 0. X vals is a one-dimensional matrix. Okay, so we already know that it's a uniform grid size, so all the delta x is the same. If it's not a uniform grid size, then what we need to do, we actually need to bring this 1 over h into the elements. Here all the elements had the same 1 over h factor, so we could factor it out. But in general, if we're doing a non-uniform grid size, then this coef for each element can change as we go from one element of the matrix to another. All right, so it's easy to extend this to a non-uniform grid size, but in general it's better to stay with a uniform grid size. So we have our y vector, all right, and it's for the initial value problem we already know y0, so our y vector, what we need to solve for is y1 y2 all the way to yn. All right, so dy, y prime becomes a matrix D times the y vector equals minus y vector plus 2x, and we bring this vector to the right, D matrix plus the identity matrix. This I is the identity matrix. All the diagonal elements are 1, all the off diagonal elements are 0, equals 2x, and the solution for the matrix is 2 times D plus I inverse times x. All right, but in reality, inverting a matrix, especially if the size is large, let's say it's 500 by 500, it's very computationally expensive, so we do not invert a large size matrix. Instead, realizing that this is a linear system of equations, we solve a linear system by, and the main method that we typically use is a Gaussian elimination. We will get back to this when we discuss linear algebra and matrix algebra in the future lectures. But in general, for a linear system, we have a very efficient way of solving the system using Gaussian elimination method, right? So we do not invert a matrix. And again, we need to impose initial conditions. Here, it's an initial value problem. So we already know y0, so we have to solve for this system of equations from y1 to yn. So from this D plus I matrix, we take this chunk from row 0 to row n minus 1, column 1 to column n. We take this chunk, and then in order to apply the initial condition, we have to modify the first equation. So here the coefficient is 1 over h minus 1 times y0, which we have to bring it to the right side and add it to this vector 2x. All right, so here's the final code. So I'm going to the y vals array. Here is n components, which represents y1 y2 all the way to yn, and then I define my forward diff operator, which basically this dx matrix, and forward diff operator based on the grid size, which is n plus 1, and the step size, uniform step size of the grid, which is delta x here. And then I define my identity matrix, which is just identity based on the grid size, the dimension. The right hand side becomes 2x, 2 times the row matrix x vals, and the operators are already overloaded for the matrix class, so we do not need to worry about that. And then the coef matrix becomes D plus I. So from the diff operator dot get dx matrix plus the identity matrix. So right now my system is ready. I have the coefficient matrix D plus I, and I have the right hand side, which is 2x. Now I need to do two things. First of all, I need to take only this block from the coefficient matrix and also apply the initial condition. So I'm going to impose the boundary condition, which here is the initial condition, here is initial condition, okay? And the initial condition is from right hand side, I'm going to set the element, so it's a 0 0 element, right? Remember, this x is considered to be a row matrix. So set element 0 0, and on the right hand side the first row is 2x0, right, the initial point. But now I need to take this coefficient matrix take the 0 0 element, multiply it by y0 and bring it to the right side. So I have to subtract this coefficient times y0 from 2x0, right? So I'm modifying the right hand side based on the initial condition for y. And now I need to take this chunk of the matrix. So I'm going to solve ay equals b, and b is 2x with the corrected value for the initial condition, and my 2D array is get block. I'm going to get a block of the original matrix. The block is from row 0 to row n minus 1, which is grid size minus grid size minus 2, n minus 1, and from column 1 to the end, which is grid size minus 1. This returns a matrix, get block, and then I call the get data method to convert it to a 2D array. And the right hand side, b, is basically 2x from row 0 to row basically n minus 1. So from row, and it's a one-dimensional matrix, so from row 0 to row 0, from column 0 to column grid size minus 2, because it's x vals, or basically 2 x vals. The right hand side is considered to be a row matrix. And I need to get the data, which returns a two-dimensional array, and it has only one row, so I just get the 0th row of this two-dimensional array, which is my right hand side, which has been corrected with the initial condition, this one. And then I pass my a coefficient, this chunk of the matrix, the b, which is the right hand side, and the empty array for the y values to a linear system object, and then it automatically solves and puts the values in this empty array y vals. And then y vals now contains the solution for y1, y2 all the way to yn. And if I want to plot against x vals, which also has x0, I need to append y0 to the beginning of the y vals, and I call the math utils arrays class inside the math utils and the concat method. All right, so it looks a bit complicated, but it's not that much. So you have to basically go through all these steps to create your system of differential equations, and then impose the boundary condition, the right boundary condition, by modifying the right hand side, and then create your system of linear equations, and then eventually solve them and plot them. All right, so here's the result. I'm solving y prime equals minus y plus 2x over 0 to 10 with y0 equals 1, and obviously accuracy depends on the grid size. Here we're doing 501 points. And I'm using the comparison here between our previous runge-kutta family, which I'm using Fehlberg. And if you recall, we implemented a Fehlberg that had the order of h to the 5, so 5th order error. So it starts from the initial point, which is at 0, it's 1, and then goes up. And as you can see, the finite difference method also gives exactly the same result. Now I think it's good if we go and look at the code. So in my ODE project, I have a new package, finite difference method, FDM, and here's my forward diff operator. It's just a class that has a two-dimensional array and keeps track of the dimension and delta x, and the constructor just takes the dimension and the uniform. So this is basically a uniform grid size. All right. And it creates a two-dimensional array and build it, and the build method just exactly does what we talked about. So this is a forward difference method. So y prime at point n is basically at point I is yi plus 1 minus yi divided by delta x. Right, this is the forward difference. So all the diagonals are -1, the off diagonals are +1, and then it can either return a 2D array that represents this matrix or a matrix object. So this matrix object is in my mathlib library in the matrix package. I have the matrix class, and we also have a complex matrix which represents a matrix with complex elements. Here the matrix object represents real elements, the elements that are real valued, all right? And it's a fairly complete class, and operators are overloaded as well. So you can just download my Git project and just use this. And then we also need the linear system solver. So for a linear system with real data, all the coefficients and all the solutions are real values. We have this linear system, and in the constructor you pass the A matrix, the array of the right hand side, and then the empty array for the solution. All right. And it implements the Gaussian elimination method. So in the solve, if you look at the details, and we will get back to this later, it's a Gaussian elimination method, and it's a very efficient way of solving the linear system. All right. So here's our example class. So test 1 is basically solving the y prime equals minus y plus 2x with the initial condition. So this is an IVP problem, initial value problem, y0 equals 1. And it's very easy. The way we implement it is very easy and very elegant. So we define our deriv function, which represents a single real valued ODE, x and y goes to minus y plus 2x. This is the right hand side. And then x0 is 0, y0 is 1, and then ODE solver, we pass the function, we pass x0, we pass y0, and then the array of x values is from x0 to x0 plus 10, 1000 points, and we're calling one of the methods such as Euler, Fehlberg, runge-kutta. I'm calling the Fehlberg, and that's it, that's done. So this is very elegant and very simple for solving an initial value problem of a single ODE. And then I'm just plotting it. So let's run. Yeah, so this is what we expect. It starts from 1, the initial condition, and it goes all the way to about 18 at 10, right? That's the numerical solution. Now let's test 2. In test 2, I'm using basically our finite difference method. And as you can see, it's not as elegant as the Fehlberg method or the general runge-kutta family, but finite difference in general is more powerful. And again, that's because you can extend it to boundary value problems, partial differential equations. It's very nicely extendable. So again, x0 is 0, xn is x0 plus 10, and then y0 is 1. Our grid size is 501, so n is grid size minus 1, right? All right. And then our matrix xval, this is a row matrix. For xval, it's a row matrix. From x0 to xn, obviously n plus 1, or the grid size, right? We have n plus 1 points or n intervals, and dx is just, it's a row matrix, so the row index is always 0, and the column is 1 minus column 0, right? So this is basically x1 minus x0. And then I'm printing the dx, the step size. And then yval is a vector, and again it only has n elements instead of n plus 1, because we already know one of the boundary conditions, which is y0, right? So y0 is known. But then our forward diff operator is still n plus 1, right? So we form the system based on all the y0 to yn, based on the n plus 1. N plus 1 equations, right? So we form the system in the most general way, and then apply the boundary conditions, initial value, final value, or any type of condition. And based on that, we throw away some of the extra equations that are redundant. and bring the known y values to the right hand side of the equation. So I have my identity matrix, which is also n plus 1 the dimension, and then the right hand side was 2x, right? The equation was let me just copy this again here. The equation is y prime is minus y plus 2x, right? So the right hand side is 2 times the x value vector or matrix, and the coef matrix is just the d. So basically this becomes d plus I times the y matrix is 2x matrix in the general form, right? So coef matrix is the diff matrix, get dx matrix plus the identity matrix. And again, the operators are overloaded for the matrices, so no worry there, we can easily add them together. And now we form this equation. Now what we need to do, we need to apply the initial condition, and the initial condition is that we bring the first row y0 from the right hand side to the basically from the left hand side to the right hand side. So we take the 0 0 coefficient of this matrix. So basically on the right hand side, so the right hand, this is the original one, 2x. We set the element ij, the 0 0 element, which is the first element of this vector, to twice x0, which is the original value, minus the coef matrix, the 0 0 element, times y0. All right, we just remove the y0 from the left hand equation, from the left hand side, and bring it to the right hand side with the coefficient matrix at 0 0. This coefficient multiplies y0, so we bring it to the right. All right, and now we have to reduce this n plus 1 equation system to n equation system. So if I'm solving ay equals b, and then this 2D-dimensional array which represent the matrix is the coef matrix, get block. And let me just quickly go back to the PowerPoint. And again, we want to get this chunk of the matrix which removes the first column, the coefficients that multiply y0, we remove them. And this goes from row 0 to row n minus 1, and then column 1 to column n. So from row 0 to row n minus 1, and column 1 all the way to column n. All right, and get data. This data just returns an array representation of the matrix, and that's because in the linear system we have to pass in an array. And then b, right hand side, again we, after applying the initial condition which bringing the y0 to the right hand side, we have to keep the first n rows, so y0 to the yn minus 1. So here I'm going to the get block, and remember it's a row matrix, so from int row 1 to row 2 they're all 0, from 0 to n minus 1, and it returns a 2D array, and it's actually has only one row, so I get the row 0. And then linear system, coefficient matrix, right hand side, the empty array, it solves the y values, y1 all the way to yn, and then I append y0, and then plot x values from x0 to xn, from y0 to yn with the red color. All right, let's run this. So our delta x is 0.02, and as you can see we get perfectly the same result, right? It starts from 1 as we expected and goes all the way to 18. So finite difference works fine, and let's reduce actually the grid size from 500, let's say 11. So our step size is 1. As you can see, the accuracy is not good as before, right? Again, the behavior is not bad, but here at the beginning it has some error. So if we go to 21, you see the accuracy gets better and better, right? And then if we go to 51, it should give us a relatively accurate result. Yes. All right, so let's do 501, and this is relatively accurate. All right, So that's how we solve an initial value problem with finite difference. And again, maybe the code looks complicated, but this is a general approach, and it has values that the original runge-kutta family don't have. And that's why finite difference is a very important numerical method in solving differential equations. Not only ordinary differential equations, but also basically partial differential equations. So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.